So, what is a linked list? A linked list is a data structure where each element called a node is connected to the next node using pointers, forming a chain-like structure. Each node contains two parts, data and a reference to the next node. The head node is the first node in a linked list. It acts as the entry point to the entire list. In this video, I will talk about three types of linked lists. In a singly linked list, each node points to the next node. The last node points to null, indicating the end of the list. This is the simplest form of a linked list. A doubly linked list extends the singly linked list by adding a pointer to the previous node. This allows traversal in both directions, but requires more memory to store those additional pointers. In a circular singly linked list, the last node points back to the head node, thus forming a loop. This type of linked list combines the features of both circular and doubly linked lists. It allows bidirectional traversal like in a doubly linked list but in a circular manner. Alright, let's talk about some differences between arrays and linked lists. Arrays have a fixed size defined at the time of creation. If you need more space than you initially declared, you need to declare a new array with extra size. Copy all the current values to the new array and then add new values. Dynamic arrays automatically handle resizing for you. In a linked list, each node is connected by pointers. When you need to increase or decrease the size, you can add or delete a node without messing with the entire list. Linked lists allow dynamic resizing. Arrays have a fixed size or require resizing with a new array. Linked list size changes dynamically. In an array, you can directly or calculatingly access the data you are looking for if you know the index. For example, to access data D3 at index 2, you can directly access it. In a linked list, you sequentially search for the data by traversing the list, node by node. Array access has O of 1 time complexity. Linked list access has O of n time complexity due to linear traversal. Array access is faster and better suited for situations where data is frequently accessed. Arrays need contiguous memory allocation, with all data placed one after another in memory. Linked lists use non-contiguous memory allocation, which can use available memory more efficiently. However, additional memory is needed for pointers. Linked list memory allocation is more flexible but needs extra memory space. Memory allocation is contiguous in an array and non-contiguous in a linked list. Inserting new data at the end of an array is simple if there is enough space. If there is no space left, you need to make a new array and copy all the current data to the new array before inserting new data. To insert new data in the middle, you need to shift all elements to the right and then insert the new data. Deleting data from the end of an array requires no shifting. Deleting data from the middle requires shifting all the elements from the right side to fill the gap. To insert new data at the end of a linked list, simply have the last node point to the new node. To insert new data at the beginning, have the head point to the new node and the new node point to the previous head. To insert a new node at a particular position, have the new node point to the current node of that position and the previous node point to the new node. Deletion in a linked list is similar but in reverse. You can try it yourself. Insertion and deletion in an array have of n time complexity if done at the beginning or middle, and O of 1 time complexity if done at the end with enough space. Insertion in a linked list has O of one time complexity if you know the node before or after which you need to insert. And deletion also has O of one time complexity if you know exactly which node you need to delete. And in the case of singly linked list, you also need to know the previous node of the node you need to delete. Linked lists are suitable for situations requiring frequent insertions and deletions. They don't require shifting elements around when adding or removing items, making these operations more efficient. Linked lists are useful when the needed data structure is not known in advance because it allows dynamic memory allocation. Data structures such as stacks, queues, hash tables, and graphs can be implemented using linked lists. Web browsers use linked lists to manage the history of visited pages. Undo mechanisms in software applications use linked lists to track changes, and it enables the users to undo and redo actions step by step.